My name is Sizhuo, and I'm a PhD student of University of Chinese Academy of Science. And this talk is about our recent work. We consider extending the S-Lemma from the commutative case to the non-commutative case. We have 4 parts in the talk, and at first, I will introduce some background of the S-Lemma and the matrix-valued polynomial, and then show our main results. And the second part is about the possibility of the matrix-valued polynomials, and then the third part is a proof of the S-Lemma of matrix-valued polynomials. And in the last, I will discuss some unsolved problems. So let's begin with a review of the classical polynomial. And in this talk, our research object is the homogeneous quadratic polynomial. So since its special form, we can define a matrix depend on its coefficients. So we use the symbol HF to denote the coefficient matrix of the polynomial f. And we can see the relation between the polynomial f and its coefficient matrix HF. And since this relation, we get the property that the fx is greater than 0 for all real vector x, if and only if the coefficient matrix HF is positive semi-definite, and it's clear. Then this is the S-Lemma for the commutative case. And as we know, the S-Lemma can be used in the general quadratic polynomials, but for convenience, we only introduce the homogeneous case here. And so first, we have 2 polynomial f and g. And then we have the Slater condition. That means there exists a real vector x hat such that the gx hat is positive. And then we can define the positivity domain, the df, the site which contains all real vectors such as fx is greater or equal to the 0. And the conclusion is with the Slater condition as assumption. The following 2 statements are equivalent. The condition 1 is the positivity domain. dj is included in the positivity domain df. And the condition 2 is there exists a positive real number lambda. Such as polynomial f minus lambda g is non-negative for all x. And the condition 2 is also equivalent to the condition that there exists a positive number lambda, such as the coefficient matrix of f minus lambda times the coefficient matrix of the g. So this is a classical for the this is a S-Lemma for commutative case or classical case. So in this page we show why the S-Lemma is important. So for the quadratically constrained quadratic program, or we call it QCQP, it is very common in the applied mathematics, but it is known as the NP-hard problem in general. So, however, when there is only one constraint, S-Lemma case. So the QCQP problem can be reformulated to a SDP problem by using the S-Lemma. So then we introduce the matrix valued polynomial, which is the kind of the polynomial in commutative case and in non-commutative case. So the first difference between the commutative case and the non-commutative case is the variables x1 to xi is non-commutative, and they also have the transpose operation. So the monomial omega can be saved as the word generated by the variables x1 to xi and their transpose x1 transpose to xi transpose. And the coefficient of the matrix valued polynomial is also a matrix. And in this talk, we always assume the coefficient is of the dimension p. But in the most case, we will assume the variable xi is symmetric, so the xi equals to its transpose. Because the variable has the transpose operation, we can also define the transpose of the polynomial. So we can also define a polynomial is symmetric or not. And then the evaluation of the polynomial f. And in the evaluation, the x is a matrix vector, which means every entry of this of the x is a matrix. And since we assume the variable is symmetric, so the entry is also the symmetric matrix. And we use the tensor product to connect the coefficient and the variables. The evaluation of the empty words omega 0 is the ID matrix. We can also define the positivity domain for the matrix valued polynomial, and we also use df to denote it. That means the site contains all matrix vector x such that the fx is positive semi-definite. And we should notice for this site, it contains the matrix valued of different dimension. So we already have some well-known results for the non-commutative polynomials. So in the 2004, Hilton and McCullough proved the positive Stolen-Zart for non-commutative polynomials, and that is if P is a set of symmetric matrix valued polynomials, and we can define its positivity domain dp, and we assume the site dp is bounded. And then we have another symmetric matrix valued polynomial q. So the conclusion is the condition the qx is positive for all x belongs to the site dp, if only if the q has such a SOS representation. And for this representation, the pj belongs to the site p or the additional site which revolves the boundedness. So in the representation, the SG or the R key can be computed by solving a sequence of SDP problems. And this is the general results. And then we have the linear keys. The Hilton, Clapp, and McCullough in 2012 proved the linear positive Stall lensas. That is L1, L2 monic linear tensors. And we also assume the positivity domain of L1, dL1 is bounded. The conclusion is the positivity domain of L1 is included in the positivity domain of L2 if and only if the L2 equals to the phi L1, where phi is a unit completely positive map. So I will introduce the definition of the completely positive map later on. And this condition is also equivalent to that the L2 has such a SOS representation. And here the Vj is a representation is a matrix. So we can compute the V1 to V mu by solving only one SDP problem. And then this is our question: how to extend the S-Lemma to non-commutative quadratic polynomials? This is a definition of the completely positive map. So for linear map phi, from the matrix space to another matrix space, we call the phi is positive if the phi maps the all matrix where M, which is positive semi-definite, to the phi M which is also positive semi-definite. And we use the symbol 1n to denote the identity map, which maps the matrix to itself. And then we define the completely positive map or CP map phi. So for all positive nature number n, the phi tensor identity map is a positive map. So we can call the phi is completely positive. And for every completely positive map phi, it has a cross representation. That means the phi M is a finite sum of Aj transpose Maj, and where the Aj is a matrix. And this is a polynomials we will use in our results. So the matrix valued homogeneous quadratic symmetric polynomials f, x, and gx. We use Aij and Bij to denote their coefficients. And similar to the commutative case, we can also define the coefficient matrix for f and g. And we always use the A and B to denote the coefficient matrix of f and g. So we'll assume f and g are symmetric. So the coefficient matrix A and B are also symmetric. So that is our main result. First main result, the theorem 1. So first, the Fg matrix valued homogeneous quadratic symmetric polynomial defined. And then the Slater condition. So there means there exists n height and then x height, such that the gx height is possible. And in addition, we need a projection P, and we should notice the dimension of P will change depend on the definition of the x, and the P has only q inches non-zero. So we can define another positivity domain depend on the projection. We use d prime f to denote this. And with the Slater condition, and the following two statements are equivalent. So the condition 1 is the positivity domain defined by the projection P of the G is included in the positivity domain defined by projection of F. And then the condition 2, there exists a non-zero completely positive map phi such that F minus phi j is positive semi-definite for all x. So we can compare the commutative keys and the matrix-valued polynomial keys. The key point of this, we extend the positive real number lambda to a non-zero completely positive map phi. And then this is our second main result, the theorem 2. In this case, the coefficients of F and G are real numbers. So we can also say the Q equals to 1. And because the theorem 2 can be same as the special case of the theorem 1. But the projection is not necessary. And the condition 1 of this theorem 2 is the dimension of the positivity domain of J and the positivity domain of F, not the D prime J and the D prime F. So the theorem 2 can be same as the straightforward extension of the commutative keys. So this is our introduction, and then I will show how to decide a matrix-valued polynomial is positive. In the commutative case, polynomial f is non-negative if and only if its coefficient matrix is positive semi-definite. We consider the same problem in matrix-valued keys. So the matrix-valued polynomial f is positive semi-definite for all x, if only if its coefficient matrix is positive semi-definite. And to prove this, we need the definition of the true matrix. And for the all linear map, not only the completely positive map, the phi, we can define the true matrix G phi of it. And we use the special matrix EAB, which has only one non-zero entry. And the G phi can be defined by this representation. And the phi m equals to the matrix whose entry is the inner product of Gij and I. So depend on the true matrix, we find there is a one-to-one correspondence between the linear map space and the matrix space. And in 1975, the Chu proved that the phi is a completely positive map if and only if its true matrix G phi is positive semi-definite. So we can say there is also a one-to-one correspondence between the completely positive map and the positive semi-definite matrix. So depend on the definition of the coefficient matrix, and there is a one-to-one correspondence between the polynomial, the homogeneous quadratic polynomial f and the coefficient matrix A of this. And we can do a rearrangement of A and then get A prime. This is the representation of the A prime. This program is a little confusing, but we should notice that we can get the A prime after unitary transform of A. So the A is positive semi-definite if and only if the A prime is positive semi-definite. And we then using A prime as the true matrix, and then we can define a linear map psi f. And it is essential to notice that the evaluation of f on x, the fx, equals to the linear map psi f tensor identity map x on the matrix x times x transpose. So we have our theorem 3. So for a polynomial f, and we have the f is positive semi-definite for all x, if and only if its coefficient a is positive semi-definite. So the proof of the theorem 3 is first, the right part implies the left part. A is positive semi-definite implies the A prime is positive semi-definite. And then because the A prime is the true matrix of the linear map psi f, so the psi f is completely positive. And then since the all matrix x times x transpose is positive semi-definite, so the evaluation fx is positive semi-definite. And then for another direction, we need to construct a special matrix vector x0, and this is x0. And then the evaluation of f on x0, x0 is positive semi-definite, implies the coefficient matrix A is positive semi-definite directly. So this is how we decide the polynomial matrix valued polynomial is positive. So then we consider the factorization of the positive polynomial. And in 2001, McClough proved the if the H is a positive semi-definite matrix valued polynomial, if and only if there exists a UX such that H equals to U transpose U times U. But we only know there exists a U, but we don't know how to construct this factorization. However, in the homogeneous case, homogeneous quadratic polynomial fx, which is positive semi-definite for all x, and we can conclude that the coefficient matrix A is positive semi-definite too, and then we can define the polynomial ux by the square root of A, and then the f equals to U transpose U times U transpose. So that's this is how we construct the factorization of the homogeneous quadratic polynomial f. So we can begin to prove the S-Lemma of matrix-valued polynomials. And this is a review of the theorem 1. And since the proof is a little long, we only introduce the key step of the proof. The first, the condition 2 implies the condition 1. This proof is easy checked, but we should notice that the linear map phi only works on the coefficient of the G, and the projection P only works on the variables of the G. So these two operations can be exchanged. And then the condition 1 implies the condition 2. We translate it to the not condition 2 implies not condition 1. And this is a condition not condition 2. For every completely mapped phi, F minus phi j is not positive semi-definite. And we can use the coefficient matrix to express it. And so for every completely linear map phi, the coefficient matrix A minus phi tensor the identity map X on B is not positive semi-definite. And then we can define the set D. And the D is the set contains the all A minus phi tensor identity map X on P, where phi is a CP map. And we use C to denote the positive semi-definite cone in the same matrix space. So we have two closed convex cones D and C. Then by the Slater condition, we know the distance between D and C is greater than 0. So depend on this property, we can use the separation theorem, and then we know there exists a matrix MIs separates these two cones D and C, and since C is a positive semi-definite cone without loss of generality, we can assume the MIs is positive semi-definite, and then we can conclude the two inequations about the inner product of the MI and the coefficient matrix. And then we want to find a connection between the inner product of MIs and the coefficient matrix and the evaluation of the polynomial. So we construct the matrix vector Xi from the special decomposition of the MIs. And this is the special decomposition of the MIs. And then for every vector we can cut it to M part. And then we can also cut the M to MIs IG. And this is a representation of the MIG. So what we want, so this is what we want. We define XIM equals to this. And in this page, we show why we need the projection P, because what we really want is only the MSIG, but we need to construct the XIM to be symmetric, so we need the projection P to get what we want from the matrix. And then evaluate the polynomial F and G at the special matrix vector Xi. Then we have the following two equations. And this following two equations is equivalent to the not condition 1. So the proof is established. And then we can know we have the condition 2, there exists a non-zero completely positive map phi such that the F minus phi J is positive semi-definite. And depending on our factorization of the positive semi-definite polynomial and the cross representation, we can write the F as a such SOS representation. So the condition positivity domain defined by the projection of J is included in the positivity domain defined by projection of F can be verified by solving only one SDP problem. And this page is about the corollary of the theorem 1. And in this case, we don't assume the variables of F and G are symmetric. And we assume that the F and G has such a special form. And then the starter condition. And in this case, the projection P is not necessary. And the condition 1 is positivity domain of J is included in the positivity domain of the F. And then multiple constraints. So in the commutative case, we know the QCQP problem is a NP-hard problem in general. But in the matrix-valued polynomial case, we can define, if we have multiple constraints, we can define a new F as a direct sum of Fx, and a new G as a direct sum of G1 to GL. Then we can apply the theorems to the polynomial new F and new G directly. And this is also a SDP problem. And then we discuss some unsolved problems. So I think the key points of our theorem 1 is the positivity domain defined by the projection P. So what's the difference between the two statements? The condition 1 of the commutative case S-Lemma and theorem 2, and all the condition of the condition 1 of the theorem 1. So with the starter condition, we know the condition 1 implies the condition 2 of the theorem 1, and then implies the condition 1 prime. But we don't know if the condition 1 prime implies the condition 1 or not. But without the starter condition, we know the condition 1 prime doesn't imply the condition 1. We find the example to show this. And for this example, and then the condition 1 double prime. In the non-commutative case, we also consider the condition like this. But the condition 1 prime is strictly stronger than the condition 1 and the condition 1 prime. And this is a simple example for this. Then last we try to extend the S-Lemma in homogeneous case to non-homogeneous case. So for the commutative polynomials, a general commutative quadratic polynomial Fx, and we have its homogenization F0, and the positivity domain of G is included in the positivity domain of F, implies the positivity domain of the homogenization of G. is included the positivity domain of the homogenization of F. And since this property, we can show the S-Lemma is still true in the non-homogeneous case for a commutative case. But in the non-commutative case, this is not true, because for general matrix valued quadratic polynomial F, and we have its homogenization F0. And for F0, the coefficient Hi0 and H0I have only one equation constraint. So there is infinite choice for the so there is infinite homogenization for F. There is an example. Fx is a general polynomial, and F1 and F2 are both its homogenization. And we can see the F1 is also positive semi-definite, but the F2 is not. So the property, the positivity domain of J is included in the positivity domain of F, doesn't imply the homogenization case in general. So we still don't know how to extend the S-Lemma for a matrix valued polynomial case to a general case. So that's all. Thank you.
Questions online?
I see a question online by participants online. So maybe I can ask you a question, Sizhuo. You hear me?
Yes, I can.
So if I understand well, one of your results was to show that if we have a quadratic polynomial, so in the matrix version, which is non-negative, then it is the sum of squares. I mean, and you give the explicit sum of square decomposition by showing that this coefficient matrix is positive semi-definite. So that's the case, degree 2 and n variables. The other case would be one variable and even degree, then the result also is true. It's a classical result. Do you know anything about the other main, the third case of, the third exceptional case of Hilbert, where you would have 3 variables and degree 4? Could you extend the classical commutative result to this setting? Did you understand the question? Did you hear me?
I didn't hear before because the connection.
I was just. Do you hear me now?
Can you repeat the? Yes, I can hear now. Can you repeat the question?
I was wondering whether you know anything about the third exceptional case of Hilbert, whether a polynomial in 3 variable degree 4, non-negative implies the sum of squares, whether there is an analog with the non-commutative case. So if there is a problem with the connections, then we need to put that maybe. Since you don't hear me.
Maybe I don't know about it.
Okay, so if there are no more questions, and maybe we thank you very much again.